started on that. Before I actually start talking about today's topic, which is our introduction to enzymes in a bit more detail, I'd like to point out that we've arranged for a review session. Lynn will be leading the review session tomorrow at 5 p.m. in Beisner Auditorium in Bowen Science Building. That's on the 3rd floor. I was going to say ground level, but Bowen has 3 ground levels. So it's on the 3rd floor, and the Beisner is one of the larger auditoriums. She'll be sending an email around with that information as well, so you'll see it twice. Again, a reminder that since we have an exam on Friday, please try to be prompt. If we're not able to seat you with everybody else, we will ask you to wait outside until we can seat all the latecomers at once. Please bring with you something that has your university ID number on it. We'll check that against what you've coded on the sheet just for accuracy's sake. We're not trying to weed out ringers or anything. We've just found that the numbers are accurate if we check them. So that's why we're doing that. It will be multiple choice and a bonus optional short essay. Are there any other questions about the format of the test on Friday? Try to bring pencils, of course. We'll supply some too, but it's hard for us to have enough for everybody. Yeah?
Is there going to be an answer key to the practice test?
No. In terms of my style of writing questions, I don't try to trick you. I may be bad at writing something, but I'm not trying to trick you. You should not take it in a malicious sense or in the most devious sense. I'm trying to ask it as plainly as I can. I may be asking you to use 2 or 3 pieces of information to think with what you have, but I'm not trying to trick you. So you should never assume I'm trying to trick you with a question. If there are questions on the sample test that you want feedback on, I or the TAs are always happy to give that to you. And I think that's the last of the sessions with you guys for the week, except for the review session. Is that right? So if you have any other questions, either feel free to email them or come to my office hours or come to the review session tomorrow. Any other questions about the cytoskeleton before we move on to enzymes? Okay, let's roll then. So we're going to approach the whole question of enzymes through a particular model. Enzymes are the secret of life in a certain respect. That is, there couldn't be life without enzymes. And almost all the enzymes in cells, in fact, are made out of proteins. And we're going to use a sort of a window to look at enzymes in their role, at least initially chymotrypsin, which makes a very nice model for that. Chymotrypsin is a pancreatic enzyme, so it's released into the digestive system, and it's involved with breaking down proteins. And its job is to take peptides like this and add water across the peptide bond. So there's the peptide bond, and when it adds water across there, you now have a carboxylic acid and a primary amine. So it's reversing what's done during protein synthesis. And it's good at this, 190 bonds per second. So 1/1000, that was 190 bonds if you had anything for lunch. It's very, very good at doing what it does. So it's over 10 to the 11th times faster than it would be without the enzyme there. So real change in the relative rate. It has a feature that we're going to see in many enzymes, which is there's a cleft. In the case of chymotrypsin, that cleft is for hydrolysis. But it's very common to see a cleft or a little valley in an enzyme that's the active site where the actual catalysis happens. This particular protein happens to have 2 domains that help to build the structure. It has a property that is another one that's common to many enzymes. It can act in relatively mild conditions. If you talk to chemists about their enzymes, they use things like platinum powder, pH 1, pH 12. These are catalysts, but they're not ones that are compatible with life. And so the fact that proteins can catalyze reactions at very mild conditions is essential. Chymotrypsin also exhibits some specificity. It's certainly not the most specific of all enzymes, but it has some specificity. And we'll look and see at how the protein achieves specificity as well as catalysis. So the rates of reactions can go, are in the absence of an enzyme, have a particular rate or a catalyst, you can make any reaction pretty much go faster by adding either heat or a catalyst of some kind. Heat is not a practical tool for living systems in general. This is just giving you a sense of the general scale and spectrum of how fast some of these things can do. These are showing you the rates under non-enzymatic conditions that I think in some sense some of these numbers may almost be fantasies, trying to come up with some way to measure how unlikely the thing is to happen. But certainly the numbers in here in the absence of the enzymes are realistic rates. And the rate enhancements you can see over here are quite amazing, anywhere from millions of times to billions or trillions of times faster in the presence of an enzyme rather than without it. Some of these, we'll be needing quite a large number of enzymes through the semester. I'm not going to ask you to learn the mechanism of every enzyme by any means, but one of the things that will help you as you meet new enzymes is that the names for enzymes are often descriptive. They'll often tell you something relevant about the enzyme. So for example, here's an enzyme that takes pyruvate, which is this 3-carbon compound. It's going to take off a carbon dioxide, so this enzyme is called pyruvate decarboxylase. It's a fairly straightforward name for it. Here's an enzyme that's going to be moving an amine group between an alanine. You can recognize the alanine here, and this alpha-ketoglutarate, which is a 5-carbon organic acid. So that amine group is going to end up over there, and that's going to end up as a carbonyl. And so what you're talking about is transferring an amine group, and the enzyme is called alanine aminotransferase. So oftentimes it's worth paying attention to the name of an enzyme because it will help you to remember what it's trying to do, and vice versa. We'll meet both of those enzymes later on. They're not picked at random. There are 6 major classes of enzymes. This gives you sort of a feeling for how abundant the different kinds of enzymes are. Oxidation reduction reactions are important. We've got over 1,700 enzymes for that. Transferases, I showed you an example of that, a couple thousand of them. Hydrolases, just breaking stuff up, so chymotrypsin is a hydrolase. Lyases can take off a group and create a double bond, so it's a somewhat unusual reaction, but there's still a lot of them. Isomerases will turn out to be pretty common, where you can rearrange one thing into its isomer. And then ligases can create a bond at the cost of spending ATP. So what is going on in an enzyme that makes things go faster? What's the underlying reality that leads to things going faster when an enzyme is involved? Let's look at something that's called a reaction graph, reaction coordinates, to look at a reaction in the absence of an enzyme. And this is a graphical representation of a very simple reaction in which the starting materials or the reactants are A and B blob and pink C. And when the reaction is complete, you'll now have a BC blob and a free green A. So that's the underlying reaction that's being represented on this graph. And here we see A, B, and C at the beginning as the reactants. And here at the end we see A and BC as the products. But to get from the reactants to the products, there's an intermediate step in which an actual structural intermediate exists. And its free energy is different than the free energy of the reactants or of the products. And we call this the transition state. It's the in transition between the reactants and the products. And it's always has a higher free energy than the other two. The difference in free energy, of Gibbs free energy, between the transition state and the reactants is called the delta G double slash. And so there's an energy associated with that transition state. And that's true of any reaction with or without an enzyme around. Now, the delta G for the reaction carries very important information. It tells us which direction spontaneously the reaction will go in. So for example, if we start with a reaction of reactants at this level of free energy, this is almost like an ecology graph, there are no numbers on it. This level of free energy, it goes through a transition state that's at a higher free energy, and then the products at a lower free energy than the reactants or the transition state. The reaction overall has a negative delta G. And therefore, this reaction is a spontaneous reaction. It can occur without the input of energy into the reaction. If, on the other hand, you look at the reactants and the products, there is a positive free energy between the products and the reactants. This one is not a spontaneous reaction. It's going to have energy put into it to go in that direction. It would only go spontaneously from product to reactant. You go spontaneously in the backwards direction. Now, this delta G for the reaction can tell you whether the reaction is spontaneous, but it does not tell you how fast it goes. The delta G is talking about whether there is a free energy change releasing energy or requiring energy being put in, but it doesn't tell you how fast a reaction goes, because that's going to be related to how big a mountain there is in the middle to get over. How high a hill separates the reactants and the products. So just looking at the delta G can tell you, will it go? It won't tell you how fast it'll go. It's a very important distinction. When you have that in your heads, we now can see in energetic terms what it is that enzymes do, what catalysts do, all catalysts, not just enzymes. What a catalyst has to accomplish is to change the free energy associated with a transition state. So here we have a reaction coordinate. Here are our starting reactants. Here are our products. The products are below the reactants, so there's a negative delta G associated with it. So it is, in energetic terms, a spontaneous reaction. But there's this mountain of energy needed to get up to the transition state. This has a large transition energy associated with it in order to get from one to the other. What an enzyme can do is create a pathway to go through that has a lower free energy of transition. Because the catalyst is providing a different way to get to the transition state, a different condition of the transition state, the free energy change associated with it is going to be less. And therefore, it'll happen more often. If you imagine a hill in front of you and you throw marbles up it, if it's a high hill, the marbles don't go over the top very often. If it's a low hill and you throw the marbles with the same wrist action, a larger fraction of them will get over the hill. So the rate overall, the number of things per unit time, the rate will be greater. The energy difference is the same, but the rate will change. Okay, any questions about this? Okay. That's a pretty nifty thing to do, to change the free energy associated with a transition state. And we're going to look at some of the ways in which enzymes can pull that off. In broad terms, all enzymes create chemical conditions of some kind or another that are going to be relevant to that transition state. Those chemical conditions are created by the overall packing of the tertiary structure, by what side chains on the amino acids are poking onto that thing. They may need a cofactor of some kind. So, for example, many of the B vitamins are found in enzymes because the B vitamins provide additional chemistry that side chains of amino acids by themselves can't provide. And we see, although there's a large universe of mechanisms, there are three very common ones that are worth paying attention to. There's acid-base catalysis, where an enzyme is catalyzing acid-base catalysis of the same general kind as the chemist is doing by taking the solution up to pH 12 or down to pH 2, but in a mild pocket where it's all under control. There are examples of covalent catalysis, where the transition state is actually chemically attached to the enzyme itself through a side chain of the polypeptide. Or metal ion catalysis, that the enzyme is holding a metal ion in just the right position in order to fiddle with the substrate. This is sort of reminding you of some of these side chains. So here we see aspartate and glutamate. Both of these are, of course, carboxylic acids. And in this form, they have a proton that they can donate. In the conjugate base form, they can receive that. Here's histidine in its protonated state. It's charged. It could donate that proton and become uncharged. Here's lysine, which is positively charged under most conditions, but that proton can move around and so on, especially when the protein can change the pKa of a side chain, which is very interesting. We talk about the pKa of the amino acid side chain free in solution, but remember we said that the protein can change the pKa of a residue in location because all the things around it. Here's cysteine. You can change that sulfhydryl, that proton on the sulfhydryl. And the tyrosine, that proton there is dissociable enough that it too can participate in reactions under the appropriate conditions. So what does acid-base catalysis do in order to catalyze a reaction? Let's think about two structures. Here's a keto structure, meaning it's got the carbonyl oxygen here. And here it is an enol version of this in which you have a double bond, the ene, and the all alcohol OH. And so you can see that between the keto and the enol form, you have the same amount of stuff there, don't you? You've got the same number of hydrogens, the same number of oxygens, and so forth, but there's been a change in pattern to it, of bonds and stuff. In the absence of a catalyst, to get from the keto state to the enol state, you need to pass through a transition state that looks something like this, perhaps. And so an electron here from this double bond has migrated out to create some partial negative charge. You've got, excuse me, I'm misleading there. The electrons have been partially withdrawn from this hydrogen. There are rearrangements within here so that there's a sharing of electrons. But you can see that here and here you have two partially negative charges. Those things are going to tend to repel each other. That's not a very comfortable state to be in. And that creates, in effect, an energy barrier to get from the keto to the enol state. How would that be different if there is an acid or a base present? Well, in that case, let's take a look. So here we have an acid present. This is a proton donor that's available to interact with the compound en route to the changeover. Here it is in the keto state. This acid here has ended up forming a hydrogen bond and partially sharing across here, so you can partially neutralize that partial delta with a partial charge of on the proton. And if that proton is then withdrawn from there, this is more easily released there. As the electrons rearrange, you have the double bond there now, and the conjugate base can withdraw, pick up the proton that was released there, and be regenerated. So you can have a rearrangement that's facilitated because the acid has reduced the steric strain of the electrostatic conditions of that intermediate. A comparable kind of logic goes on to do the same reaction. We're still starting with a keto group to the enol group here, but in this case, how a base would go about doing it. And in this case, the base is coming in to pull off a proton first, and a proton from the water can come in and reconstitute it that way. But the logic is similar. But the idea behind that is that acid and base can facilitate that rearrangement. In some cases, there isn't just a interaction, electrostatic interaction at the level of protons and hydrogen bonds and stuff to the substrate or the transition state. sometimes there's an actual covalent bond made to the substrate that is then broken to release the product. And what might that look like? So this is an example. This is one example of that kind of a thing. In this case, we want to go from an acetoacetate. So this is, in effect, two acetic acid molecules have been smooshed together. And here you can see it has the carboxylic acid group, and here's the carbonyl oxygen. And where we want to get to is a 3-carbon compound that's lost to carbon dioxide and has still the carbonyl oxygen there. To do that, as these electrons rearrange here, the carbon dioxide coming off is not too difficult to imagine, but to get to this particular state, there's an enolate transition intermediate. So in other words, a double bond was created here when the electrons moved over, and a negative charge up on the oxygen from the electron moving out. And then that would need to receive a proton and rearrange to give you the carbonyl oxygen and the single bond there. By contrast, if this happens through a covalent intermediate, it would look something more like this. You have here's your acetoacetate entering in, and you have an amine group available through a side chain from the peptide back from one of the side chains on the polypeptide, and that nitrogen then can react instead, and you end up having a covalent bond, still a double bond like the carbonyl group, but now a double bond to the nitrogen, and this is called a Schiff base. And this Schiff base then can undergo rearrangements. So you can see that the Schiff base then allows for the loss of the carbon dioxide. But in this case, the Schiff base is the intermediate instead of having an enolate intermediate. And so when the proton comes in to react with the Schiff base, you can then have the release of the acetone, and you reconstitute the original amine group that was the side chain on the amino acid. So in this case, by having a covalent attachment to the enzyme, you've been able to avoid a transition state that would have been awkward otherwise. This is what covalent catalysis can look like on a reaction coordinate. There are generally 2 energy barriers because you actually have 2 states you're going to have to get through along the way. So if you start with your reactants here, there'll be a transition to get to the covalently bonded intermediate, and then a second transition to get out of that down to the product. But what you've done is to break down that barrier into 2 steps so that you don't have as large a step to go at either one. We've seen these amino acid side chains in the past, and that's because they are among the ones that have potential for polar groups and for participating in this kind of catalysis. So both serine and tyrosine are alcohols, and those alcohols can exist in 2 states. In this case, it could withdraw a proton. In this case, it could donate a proton. And their reactivity then will depend on which of the 2 they're in. And they're also, for that reason, not just potentially acid-base catalysts, but also potentially a residue at which a covalent catalysis can occur. Let's talk more specifically about one particular enzyme, one that actually works. And let's talk about chymotrypsin. Chymotrypsin is a nice example to look at because it is an example of both acid catalysis and of covalent catalysis. So although it's just the one enzyme, it takes part in both kinds of catalysis. I already mentioned that chymotrypsin is a protease. It can digest peptides into pieces. And you might wonder, how do they figure out how chymotrypsin digests proteins down into fragments. Well, it was through a series of compounds and other kinds of studies. DIPF, or diisopropyl fluoride, you don't need to know the exact meaning of it, is a reactive compound that can react with serines. And it was found that it reacted with serine 195 specifically. The other serines in the enzyme were not affected, and when it reacted with serine 195, it was no longer a catalyst. So this pointed to the idea that serine 195 was somehow an important part of the catalytic mechanism. It's in fact so important that we now know that chymotrypsin is one member of a family of serine proteases. So serine has an important role to play in a number of different proteases. Another compound called TPCK could mimic substrates to some extent, and it reacted with one histidine in the molecule, histidine 57. So that was two members now of something that might end up being the catalytic site. The third important member of the catalytic site was identified through crystallography, which picked out aspartate 102. And so now we have three residue side chains that are going to be playing a role in catalysis. Just a comment on nomenclature here. This is one way of talking about protein structure. So SER195 means serine at the 195th residue, histidine at the 57th residue, and so forth. So one thing that should be striking about this is that these three side chains are coming in from very different parts of the primary structure. So it's 57, 102, and 195. The three side chains are coming in from very separate parts of the primary sequence. That's an important aspect of the folding up to get a correct tertiary structure, that overall folding in space brings together the side chains of residues to create functionalities of all kinds. So this is another example of how it's the folded protein that's functional, not the unfolded protein. It turns out that this particular group of three, the gang of three, of aspartate, histidine, and serine, occurs in more than one enzyme. This is not just unique to chymotrypsin, but it's a fairly common pattern. So it's called the catalytic triad. And the catalytic triad is going to turn out to be the actual mechanic that's going to go in there and actually change the covalent bonds. You can see that as at rest, so to speak, there's hydrogen bonds formed between the members of the catalytic triad. So what does this look like? Okay. I'm going to look at this mechanism in considerable detail. I don't expect you to know it in as much detail. I will try to highlight the most important features as we go along. But I do want you to, at least once in your lives, look fairly closely into the inner workings of an enzyme, because this is an important part of how living things get things done, and of what needs to be known in order to do things like design drugs, design inhibitors for viruses, and so on. So let's look. We have here spread out the catalytic triad. We have ASP102, HIS57, and SER195, or ASP, HIS, SER. And here's the substrate moving into the active site. All right. This is the substrate, and it's by diffusion, it's come into the active site. And there's one specific bond that we want to break. So this bond here between the nitrogen and the carbon, this is the carbonyl carbon and the amide nitrogen. So we want to break that bond specifically. They call that the sessile bond. And sessile means bond that can be broken. Scissors cut things. So a sessile bond is a bond that is going to be cut. And it's going to enter the active site in such a way to come close to the oxygen of SER195. And in doing that, by coming close to there, it's going to remove the proton from the serine alcohol. I'm sorry. Excuse me. I take it back. I don't know what notes you just took, but back off a second. The removal of this proton by the histidine, the removal of this proton by the histidine is going to generate an O minus here that is then going to become, is going to be able to attack the carbonyl carbon in the substrate. So we want this oxygen to be able to attack this carbon. The proton here is going to be over on the histidine. You can see now it has a positive charge from the proton it's picked up. So this oxygen is going to form a covalent bond here to the carbonyl oxygen. This covalent intermediate is a tetrahedral intermediate. So if you look at that carbon, it has all four bonds are occupied. In the substrate, back as a carbonyl oxygen, it has it's bonded to 3 atoms, so it's not in a tetrahedral shape. When we have made that covalent attachment to the serine, it is now a tetrahedral, covalently attached transition state intermediate. The next thing that's going to happen is that the histidine, which has this extra proton on it now, is going to donate that proton. So in other words, the histidine is now basically acting as an acid catalyst. It's going to donate a proton. And by donating a proton here, that's going to have this bond break, and we'll end up having the sort of the left-hand part, if you like, of the substrate departing as a new peptide fragment with a free amine end. The right-hand half of the intermediate, so to speak, is still attached to the serine, however. Here's the catalytic triad, aspartate, histidine, serine, and we still have the other half of the substrate covalently attached to the serine. This is called the acyl enzyme intermediate because this is an acyl group now. It has this double bond to the oxygen. So this is a tetrahedral intermediate. This is an acyl intermediate. So there's 2 different covalent intermediates in this catalytic pathway. The next thing that needs to happen is for water to enter the active site. There are actually a lot of enzymes in which water is an essential part of the catalysis, and yet in many cases it's not actually drawn into the reaction. So if you're ever puzzled by an enzyme reaction that's being drawn, I would suggest you might want to see if there's a water molecule that wasn't taken into account of. In this case, water is going to come in. The water can donate a proton to the histidine. So the histidine is a proton acceptor, or it's acting as a base catalyst. And that will leave a hydroxyl group that can then attack here. And when that has happened, we can get the reverse of, we've regenerated a tetrahedral intermediate that looks like this. And the same general movements can occur. And in this case, instead of becoming attached to it, it's going to become detached from it. And the left-hand half of it, if you like, can depart as a carboxylic acid. I've duplicated this diagram so that they're large enough for you to be able to see them on the handout. And if you look now, what we've done is we've completely regenerated the catalytic triad of the chymotrypsin. So all of the 3 residues have gotten back to their original state. Everything has been restored to where it was. Let me just take a second. Okay. So if all the action is happening at the catalytic triad, if it's the asp, his, SEER that are doing the actual work, that are moving protons around to be acid-base catalysts, that are making covalent bonds to make a covalent catalysis, what's all the rest of that protein for? Certainly one part of it is to position those residues in the right place. That is certainly one important role of it. But that doesn't seem like quite enough information. One of the early proposals for how an enzyme acted as a catalyst was the notion that they fit together as nicely as a lock and a key. And while that had a certain attractiveness initially, there are some because it could account for the specificity. We haven't talked a lot about the specificity of chymotrypsin yet, but we're going to see that in a bit. If it were really this tight and this specific, how would products fit? And would you actually end up having a situation like this, where you could start off with substrates, and if the substrates bind too tightly to the enzyme, actually have a larger free energy change to get to the transition state than you would have had otherwise. So in its rigidity, the earliest model was probably not quite right. Part of our understanding now is that enzymes can stabilize the transition state. It's not so much that it's a lock and key for the reactants. It's that the enzymes interact with the transition state to contribute to its stability, and that makes it a lower energy barrier to get to the new one. So let's compare these two little active sites here. We again have the ASP, the His, and the SEER at the active site, the catalytic triad. And this diagram is comparing what would happen in a normal chymotrypsin here to, what happens between the entry of the substrate. So this is the substrate entering, and this is the tetrahedral intermediate. And part of what's happening in this tetrahedral intermediate is this oxygen is stabilized by low barrier hydrogen bonds to that oxygen. And these low barrier hydrogen bonds are therefore reducing the energy it takes to get to that point. This may be a little confusing here. The N of the glycine would be probably the N of the amide nitrogen, not of, there's no side chain, so it couldn't be from that. Some of the other things that specifically happen in chymotrypsin, the aspartate, which we hadn't actually heard doing anything so far. We heard of both the serine and the histidine acting as acid-base catalysts, but we hadn't heard about aspartate doing anything. Aspartate can form a hydrogen bond with His57 that simply lowers the energy barrier for that proton to be transferred. And so picking up the proton at histidine is simplified by the fact that the carbon, the oxygen in the aspartate is aimed directly at the other hydrogen and its other nitrogen and its hydrogen. If we think about enzymes in general, and partly as chymotrypsin as an example and partly drawing on our knowledge of enzymes in general, some of the other things that enzymes do to make catalysis happen are proximity. They hold reactants closer to each other. And that sounds like a trivial thing, but in effect, what an enzyme does when it holds two reactants closer to each other is it's changing the concentration. So it's a way to very greatly change the effective concentration without having to change the actual concentration. Because enzymes can hold substrates in particular positions, they don't just sort of hold them flopping around like a billiard ball in a pocket. They hold them in a particular position. Because they do that, they can orient the substrates so that the different parts of the substrates are aimed correctly for the new bond that needs to be made or broken or changed. So between these two effects, proximity of holding things closer together and orienting things, we can get about a 1,000-fold enhancement of rates just from that. Now, we saw in that initial table that that's not yet enough more to account for many of the enzymes. Many of the enzymes we're looking at had 1 million or 1 billion enhancement in rate. But that still is, we're partway there. Another aspect of what goes on is what's been called induced fit, that the enzyme starts off with one particular shape, and that the binding of the substrate leads to the enzyme changing its shape often in subtle ways, but important ways that then rearrange what's going on around that substrate. There can be electrostatic catalysis, where the surface of the active site is organized in ways to create electric fields around things. Another contribution is that in active sites, for the most part, water is not present in an active site. There will be provision for it if it's part of the reaction, but if the reaction doesn't actually involve water, in general, the substrates will be dehydrated when they're held in that active site. This is part of why, even if you take out some of those some of those catalytic triad side chains, you can still get some enzymatic activity, because you can get the proximity of the orientation and the dehydration effects to occur in the absence of the catalytic side chains. So let me just take a look here. Okay. Any questions so far? Okay. Let's take a look at another enzyme that will turn out to be extremely important. Hexokinase is an enzyme of the glycolytic pathway. And its name is telling you that it's a kinase, so it's going to add a phosphate to something. It's a hexokinase, so it probably adds phosphates to hexoses, 6-carbon sugars. And for the reaction to proceed, what has to happen is that glucose will bind. This is an empty hexokinase. And when glucose binds, there's actually a movement of the enzyme to close it like that, sort of like a clamshell closing down on it. So if you compare the unoccupied and the occupied hexokinases, you can see there's pretty large conformational changes on the binding of the enzyme, the substrate. And part of what it's going to be doing by doing that is, in fact, by sort of squishing it into this sandwich of enzyme, it's desolvating. It's removing the water that would normally be around the hexose. Now, if you think about hexoses, glucose is a hexose. All those alcohol groups, it's a very polar compound. There's a lot of water around that thing that needs to be removed before hexokinase can have just that thing going on without having to worry about competing reactions where water could come in and break down the ATP and have nothing to show for it. This is showing you chemically what we want to have happen. Here's your hexose, the glucose with its alcohol groups. Here's an ATP molecule. And the desired result is this, with a phosphate up there and an ADP released. If there was a lot of water in that active site, you might well imagine that it could compete for the phosphate from the ATP. When we talked about myoglobin and hemoglobin, we talked a little bit about their evolution, the fact that if you look at their primary structure, their sequences, there's a lot of differences. Their secondary structures were all alpha helices. Their tertiary structures were very similar between myoglobin and the hemoglobin subunits. And then only the hemoglobin had quaternary structure. The proteases show something rather similar. Here you can look at the tertiary structure here of 3 proteolytic enzymes, chymotrypsin, trypsin, and elastase. So these 3 are all proteases, but they have different functions to perform in the body. Chymotrypsin and trypsin are both digestive enzymes. Elastase is more of a tissue protease that's used in remodeling things. If you compare these 3, their primary sequences, their primary structures are quite different. There's a lot of differences. However, the aspartate histidine serine is conserved. Those 3 residues for the catalytic triad are preserved in all 3 of them. The residues on the surface vary quite a lot. Their only job is to be water soluble. So it really doesn't make a whole lot of difference whether you've got a glutamine there or an aspartate there. You know, as long as it's something fairly water soluble, it'll accommodate it pretty well. You can also see here that most of the secondary structure is similar, although it's not quite as close as it was for the hemoglobin and for the myoglobin and the globins. And now, the chymotrypsin family is not the only family of proteases. If we go to bacteria, there's an enzyme called subtlysin because it came from B. subtilis. And its tertiary structure is quite different. Let's just flip back and forth a little bit. So try to eyeball this into your head of what it looks like. This is the chymotrypsin family. And here's the subtlysin, really quite different tertiary structure. So primary sequence is different, secondary sequence is different, tertiary structure is different. However, look at this here in the core. There's still a cleft, and in that cleft, there's still this aspartate histidine serine. And this is still the catalytic triad in the subtlysin family. This is an example of what's sometimes called convergent evolution, where the same solution comes up more than once. This is such a good solution to the problem of digesting proteins that there are 5 different families of proteases that have this particular catalytic triad, even though their primary structures and their tertiary structures have no resemblance. They're clearly separate families. Okay. Well, I think we're coming close to the end of time for the day. Do people have any other questions about the test between now and then? Okay. Let me just turn off the recording.